Hello and welcome to this video about reaching even richer C++ in OpenCL kernels with use of libclcxx. This video is recorded for IWOCL 2022 and it's presented by Anastasia Stulova and co-authored with Ishfaq Vardak. C++ for OpenCL kernel language that was released a few years ago brings C++ capability to OpenCL kernel development. However, it's still missing C++ library support. And because modern C++ standards are extended more and more using C++ libraries, it is an important limitation to address. In the previous work, we looked at porting functionality from libcxx project, which is a production quality C++ libraries residing in the LLVM repository. And we have successfully enabled type trait to be used with OpenCL. However, its use is not straightforward from libcxx project because it's missing OpenCL target and it also doesn't contain OpenCL-specific type traits. Therefore, libclcxx project has been bootstrapped, and it is a public GitHub repository containing C++ libraries for OpenCL, and the goal is to gather more and expose more of a C++ functionality to OpenCL kernel developers. It integrates libcxx project, and it is made to work with Clang frontend. Type trait is the first library made available in this project, and we have added quite a lot of tests for the new functionality, and we also integrated the testing into continuous integration for the future development. We also provide Doxygen documentation in very similar style to C++ reference pages, hoping that it will help developers to navigate throughout the new functionality that we provide. In the following few slides, I would like to spend a little bit more time to dive into OpenCL type trait library. Type trait is an essential library to facilitate fully metaprogramming in C++. And this new library is inherited from libcxx project, therefore all the type traits from C++ can be used. We also specialize some of the C++ type trait for OpenCL-specific type system, and also add some custom type trait for OpenCL, for example, for vectors, address spaces, images, or half precision floating point type. And thanks to reuse type trait implementation from C++, we have shortened the development time, and we also guarantee maximum compatibility with C++ standard. Let's look at the internals of this OpenCL type trait library. First of all, it is a header-only library. And this is just an example of how it is implemented, taken from the implementation in the repository. At the beginning, you will find this include of type traits, which is a standard C++ type trait from libcxx. It is enclosed in the extension, which is a Clang extension, as you can see. However, it doesn't result in any non-conformant functionality in the application code. If you are interested to learn more about this functionality, I will refer you to our previous publication at IWOCL last year. Then we extend namespace std, and we provide some of the specializations for the existing traits. In this example here, you can find is signed and is unsigned, and it is specialized with OpenCL vector type int2. And we reuse existing C++ type traits such as true type or false type to implement the new type traits, which is great. And in this particular case, in our Doxygen documentation, we just refer to C++ reference because we don't actually change the core behavior of C++ in these traits. Here is another example where we are adding new trait, vector size. This trait will have a member value corresponding to the number of vector elements in case a type is a vector, and otherwise it will just have 0. We use integral constant type trait from C++ to implement it, and as you can see in the definition of this new template, we use value 0 to pass to integral constant template. And in all the specializations that we provide for a concrete vector with a fixed size, we will just pass the size of a vector in this a second template parameter. Let's just look at some examples as a demonstration to show how this type trait library can be used today. In the first example, I will demonstrate address space traits. Let's first look at the last 4 lines of this example over here, where we are defining function bar that takes 2 input parameters. They are both pointer and they are different pointer types, global int and float and local float. Then we will be using a foo function with both pointer types. And in order to implement this function, the most natural way in C++ is to use templates. This template function foo will take a template parameter type, pointer type. And it is very common to use a pointee, the type that pointer points to declare a local variable inside this template function. Normally what you would do in C++ is you would use a remove pointer type trait. And you would query the member type from this type trait. And in this case, we are creating a type alias over here. In C++, you can just use this pointee type to declare a variable, but it's not going to work in OpenCL. And the reason is that our pointee type here, as you can see, has an address space. And the address spaces here are global and local. And the only address space allowed for local variable is actually private address space. So we have a solution to this problem now. If we are using OpenCL type traits, we can just use remove address space type trait and pass our pointee type over here and then query its member type, which will have a pointee type without address space. So the address space will be removed. And now we can succeed declaring our local variable and we can use it to do whatever we need to do with it. A slightly more complex example with use of vector type traits. In this case, we are computing a reduction over n elements and we are performing some reduction. This is an example of kernel implementing this reduction. It has input and output buffer as parameter and it also has number of elements n passed into it. The input and output buffers are made generic with respect to the type that they contain. And now inside the body of this kernel we have a loop, and in this loop we just iterate over elements in the input buffer and we sum them in together, and then we will write the result into the output buffer. The position of the input buffer and output buffer will be different for different work items because they will just perform certain subset of these computations. And the offset in the buffers will be determined by the position of a work item in the computational grid. Something important to highlight that we can make this implementation of reduction fairly generic such that we can, for example, exploit vector accesses. And in some OpenCL accelerator, vector accesses can be just much more performant. Let's just look at how we can compile this example using clang. Over here, we are passing a new include path to the libclcxx include directory. And we also pass a type as a preprocessor macro. And this is how we make this implementation of reduction kind of generic with respect to type. We can pass a scalar type or a vector type. And if we pass a vector type, then this case over here will be applied and the computation will be performed using vector accesses. Let's just complete our example. First of all, we will include OpenCL type traits. And the first trait that we will be using is a vector size trait that was introduced just a few minutes ago. We pass the type, which was given in this command line argument over here, and we will query the value. This will correspond to the vector size if the type is a vector. If it's not a vector, it will be 0. Then on the line 3, we will declare a type alias and we will use scalar type trait. This is a new trait and it will allow to query the element type of a vector if a type is a vector. And if it's not a vector, it will just be an original type passed into the template here. On the line 4, we start definition of our add_lms function. It takes a pointer to the buffer, and then inside it actually has different variants. But the variants are actually expandable at compile time because they are enclosed in the const x per if statements. What do we have as a condition of these statements? We have a vector size as a condition here. And what does it mean? That for different vector sizes, we will choose different implementation. And in this implementation, what we will do, we will perform vload. For example, for 2 vector elements, we will use vload2, and then we sum 2 components and return it as a result. We will do the same for all other vector sizes. And if the type, which was passed in as an argument during the compilation, it's not a vector type, we will just return one item from the buffer. That concludes my example. And at the end, I just would like to summarize that we have created a space for C++ libraries for OpenCL. And the first library, OpenCL type trait, is made available, and it's derived from libcxx for a maximum compatibility with C++ and also reducing the development cycle. Developers are invited to experiment and to contribute as well. And we appreciate any feedback about either the libraries that you would like to see next or any bugs or missing features so far. And please provide your feedback using libcxx GitHub project page. You can just create a new issue or just join a discussion on an existing issue. Thank you very much. And if you have any questions, I will be happy to answer them on the dedicated IWOCL Slack channel.